thank you for being here, folks. And yeah, we're going to talk about Solid. But the things we're going to talk about here are like, I think 80% of this talk is actually about signals, more than Solid itself. So pretty much everything that this 80–90% of this talk is going to be transferable for all the frameworks that have signals. The idea is to give you like a nice insight about what are signals and how they work and etc. But before I start, like this awesome, this stage and the screen is awesome, and I just need to apologize first because I'm half Italian, half Brazilian, which means I kind of walk around and I move a lot around. So I'm a little bit scared of standing in front of the slides. So if anything, like if I'm standing in front of something you want to see, you can just like use the force and I'll just jump. So I'll see you. Sorry about that ahead of time. But yeah, and if by any chance we don't have times for Q&A, I'll be floating around, and I love talking to people. So please just, if there is no time, or if I didn't get to answer your question in here, just grab me at a coffee break, and I'm happy to talk to you about it. But yeah, so before we start, let me just give you like a brief intro about who am I. I work as a developer relations lead at a company called Crab Nebula. We are the companies from the founders of Tauri, which some of you might have been to the workshop I gave before. And I'm also a GDE for web technologies, and I'm part of the SolidJS team. So that's a little bit about me, about how I got into signals and so on. And if you have any questions or feedback or whatever, or you want to see like some of the content I create about it, I'm always doing this kind of stuff. I prepare some like easy to find redirects, because naming things are hard, and I just switch handlers on every social network. But anyway, yeah, signals. So except for this one little stubborn one, pretty much all frameworks now have signals. And can you please raise a hand if you work or you consider yourself a developer of one of these 5 ones here, so just so I know who I'm talking to? Yeah, awesome. So cool. But to the people that are hearing about signals for the first time, or have started talking about signals, or anyway got interested in that, the first conversation that I have usually go like this: signals. And then somebody like, what the heck are that? And then people go like, oh, fine-grained reactivity, signals, fine-grained reactivity. They're like, and then people are like, yeah, what the heck are fine-grained reactivity? And then people say, yeah, signals. And so before we talk about it, let's just level the ground. And then for that, to properly understand what signals are, I think we need to talk about API architectures. And fundamentally, the API architectures are 2. We have pull systems and push systems. Pull systems are like, for example, when you have the data, and then you have a component that is fed on that data, and he's like, okay, do you have updates? No. Do you have updates? No. Do you have updates? Yeah. And then you get an update. That's a pull system. Push system is when the data updates and you just stuffs it into the component. So this kind of system, like both of these systems have their pros and cons. Like none of them is good, is a silver bullet for anything. Like on the components, on the pull system, you need to have some kind of polling, and you have the con that your component is not aware about the data is not aware about where it's been used and not. So you need to do all that checks on your logic side. And on the push system, because the data doesn't know how the component works or what stage is your system by the time it updates, there is something called back pressure, which means that there is a situation where the data updates can be so frequent or so large that this is going to stress your system to the point that it can crash. So after that, we also have a little bit more complex system, which is called push and pull. Some people refer to that as push then pull, but you're mostly going to see them described as push pull. So in the push pull, you have the data in the component as well. And what happens is that the data notifies the component. Oh, I have an update. And then the component, when it's ready, says, yeah, send me up and I'll use it. So that means that the data can notify the component that's got, so the data knows where it's being used, and the component can decide, okay, now is the time that is best for me to get it, so it doesn't stress your system. Just to be crystal clear, the pull system is what React developers are using right now with use state and stuff like that. This is a pull system. And the push-pull system is what signals are. Signals are an implementation of push-pull systems. So push-pull systems make things reactive. The concept of reactivity is that your component can actually understand the data and act accordingly. So if you get to somebody that's like a reactive extremist, they can even go and say React's not reactive because of that. But I'm not here to stress people out. Signals are an implementation of push and pull. And on the signals implementation, it makes things fine-grained. Does it mean you need to have signals to have fine-grained reactivity? No, you probably can get it by with something else. Does it mean that every push-pull system are fine-grained? No. There are some requirements to be fine-grained reactivity. And I try to summarize them in two main things. The first one is efficiency. So your system, to be fine-grained reactive, it needs to do only the work that it's required to do, not more, not less. And it needs to be glitch-free, which means it should never show you an intermediate state. We call that state tearing, when you have like, everybody here uses GitHub, right? Yes, yes? So are you familiar with the time where you go into like a pull request page and you're reviewing the pull request and you see like there's a counter up on the top and says, yeah, we have 10 pull requests open, and then you merge one and then you go back and the pull request list page says you have 10 open but the list has 9? That's state tearing. That means there is an intermediate state being shown to your UI. And that's a glitch for a reactive system. So to have fine-grained reactivity, you need to be free of, well, you have to be free of that. So to summarize, you have push and pull, you implement push and pull, and then with signals, and then you reach fine-grained reactivity. So first question for us is, can you actually achieve fine-grained reactivity without push and pull? Right now, today, I'm not aware of anything that can do that. And that's where we get to our first little example. So in this case, I try to abstract it as much as possible. So it looks like React, but yeah, anyway. So let's render this. And so if we render this button, and this button is one that, like, on click, it's going to update, and show that that count on the DOM. So once we click that, what happens on this kind of stuff when there is a VDOM in the pull system, because the data is not aware, it needs to run the whole thing all over again. So what gets re-executed is actually the whole thing. So you get the state re-execute, you get all the function body re-executed, and you have the whole rendering of the entire component re-executed. On the other hand, if you have something like signals, when you render the button and you click it, the thing that gets updated is just that little function call there, and that's why it's a function call. That's the difference between storing a value as a reference or using the getter of that value, and that's why they're a function, because that means that value does not exist per se in the rendering thing. What happened with has in a rendered artifact is a call for that value, which means that every time I say this function needs to re-execute, it's going to fetch a brand new value for me, and just that. But on my slides, I can do whatever I want, right? So let me show you, actually. Oops, that's something else. So what we get here is I have this, this little code sample, and cool. You don't need to look at the terminal. So this one, as you can see, I'm using the brand new React compiler that's supposed to, that reduces a lot of the re-rendering work that React does under the hood. And I have this little app. And this little app over here has this function. Everybody can see it? Cool. Do I need to make it bigger? Maybe a little bit bigger, yeah. And it's just cutting some real estate here for some reason. Let's see. Now it's a little bit better, right? So what this function does is just like do some big work. And I'm going to say that it's going to take a name and it says, yeah, it's just re-rendered this particular name over here. And then I have this count. And first, on the top app, I'm going to log that it's being rendered. And then I have the first component, and I have another component. And what happens is that the first component actually calls a second component that is just passing down the props. So technically, even if the props change, it hasn't affected it. So it can be memoized and so on. And the component number C is actually just rendering D. And D is the one that actually has the button. So as well, like A and C are supposedly not being affected by any kind of data change and whatnot. In the same way, I have the same implementation with signals over here. So let me just try to reduce my screen. So as you can see, it's basically the same. I just had to change a little bit of the syntax because, as you know, like as I just mentioned, we passed the accessor, so then it's just a function call and so on. So the thing that's important for you to see is actually in our console. So let me make it bigger. So on my right-hand side over here, you see React with this, sorry, excuse for the React logo, and the solid one. So now I'm going to refresh it, and you see all the apps get rendered for the first time, all the components, I mean. And same way in React, all of them get rendered in the first time, and we clear it out. And remember, to be fine-grained, you need to only execute what's needed. So in this case, I'm going to click the increment, count's going to change, and we need to only re-execute the clicked event, right? So I click, I get the event, and everything re-renders. And in Solid, or any other signal implementation, to be honest, if I click here, only the click is executed. So that's the difference between what fine grain is supposed to be and what coarse grain is supposed to be. So the efficiency is that I only execute the function that I intended to execute my user in this case. Cool. Back to our slides. And so with that, I reach what I call the golden rule of developer experience, because developer experience is just a bogus name if it's not about UX. So the golden rule of the developer experience is we create good defaults that lead to our users or framework users to have good code, and then you can actually worry about the things you're building. So that leads to good DX, okay? So this summarizes it all. You're all signals experts right now. That's all the conversation about what are signals, what are fine-grained reactivity, and so on. So that means we can now dive a little bit deeper and go deeper into the difference between different signals. So remember this? We have pull, push, and push and pull. And we already know that push-pull is what signals are. But as I mentioned in the beginning, not all signals are created the same. There is one fundamental difference between different implementations of signals. There is the lazy signals and the eager signals. So let's check about like the difference between them. So let's say, for example, this is like my oversimplification of a common problem you have on fine-grained reactivity. It's a kind of a simple one to describe, but it's the toughest one possible to solve with fine-grained reactivity, which is when you have a component that has the diamond problem, we say, when a child depends on the derived value of a parent and on another parent. So when can we, like, if both of them update, how do we update the child only once? Or how does the child knows that the other one doesn't have, and so on. So that's the reason why this problem is so tough, is because if you update the child too eagerly, the mom updates, the child updates, but then the dad also updates, which means you have an intermediate state. And as I showed, as we talked before, that's a capital sin for fine-grained reactivity. So on lazy signals, the way it solves is the mom updates, and then the child says, okay, give me the update. But then the mom holds the update until the dad actually says, no, I don't have an update, or I am ready to give the update as well. And then on a layer by layer, then the child gets the update. That's why we call them lazy, because they wait on each other. On eager signals, what happens is the mom says, I have an update. And then what happens is that the child says, okay, give me the update, and immediately goes to the dad and says, okay, do you have an update? And then the dad says, no, I actually don't. So the eager signals invert the control, where the child actually goes to the other parents to check the state where they're in. And that's the main difference between the different implementations of signals in this case. So again, in my slides, I can do whatever I want. So let's take a look about how Solid works in this case. Okay, so this is not, where is it? Here. So this is, so this is something that, oops, I'm sorry, I'm very inadequate with this trackpad. This is too big, I cannot see everything. One more, yeah, cool. So this was created by one of our core members in Solid, Milo. So he's one of the people that worked the most about the internals of how the Solid core works, and just a genius about reactivity and whatnot. So he made this code. This is actually like very interesting code. Unfortunately, I would need a second, maybe a third talk to go into like how this code actually works and behaves. Like there is like a bunch of generators around that handles all the updates and whatnot on this. So where is it? Where is it? It's actually quite interesting. Where do I get it? Where's my code? Seriously, I got lost in my own code base? No. So this is actually a class that creates a reactive system, and then we manage like the cache state, and we manage like all the all the internals, and then you have one to get the state of the parent, you have another one to set a new value, and you have other ones to basically determine if it's a stale cache or it's not, and so on. So there's a lot of like a lot of things that go around on making this thing ticks. So as you can see, this is a dependency graph, which means that once I update A, I determine that C, because it's a child of A, is possibly stale. So it enters a state of checking the cache. It actually enters a state of dirty cache, And then because D is a child of C, and C has a dirty cache, it says, okay, D, maybe your data is also stale, so maybe you also need to check. Then we go further, and because F is also a child of A, it's also dirty. And then because F is dirty, G is possibly stale. So then because G is possibly stale, that means H is also possibly stale. So our system now knows there's tons of work to do. And then B gets updated as well because C pulled it off. And then because C updated, D got the news that, yeah, it was actually C got updated, so I also am definitely dirty, so I need to clean it up. And then D needs to update, it cleans it up, F updates, which means G updates, F is finally clean, that means G can update. Because G updated, H updates, G is finally clean, which means H can update and get clean. So that's like the whole principle about the diamond problem, and this, of course, happens much, much faster. We're just like going step by step, so you can understand like how complicated it can be to make sure that your data works both ways. So your child knows that the parent got updated, and then it can start pulling stuff on. That's how the eager system works. And where's my slides now? Back here. Awesome. Cool. Everybody up to speed so far? Yeah? Okay, awesome. So why am I talking about eager and lazy? Technically, signals are all the same. Fine-Grained Reactivity is all the same. As I mentioned, there is like a small little difference in this case for the end user. But my point, and I might be biased because I work with Solid on my day job and I'm part of the Solid team and so on, is that eager is actually easier to understand. And that's like one fundamental thing, because of the eager thing, we can then work better with our scheduler. And that's the part that kind of leaks into, the abstraction leaks into you that are using the frameworks, where with this, like with the scheduler means that inside the framework, there's an update, so the framework needs to then decide when things are going to re-render. And because signals are lazy, or with lazy signals, you need to schedule everything to the end because data takes longer to update. But because we have eager signals, we can actually invert that, and we then, by default, all updates happens in the tick, but we can actually batch them. And if you're not sure about that, if that's like too abstract, let's debug something. So, you know, there are two kinds of developers, and I want you to help me with that. I want to raise hands everybody that uses console log to debug. Yeah? So that's one kind of developer. The other kind of developer are the ones that don't like to raise their hands, because I see you. So let's say, for example, I have this component, and this component has an update, has a signal that's updating the data, and then you have a derived signal that just takes whatever got updated and doubles it. And then by the time that I'm updating it, right immediately, I want to console log, because sometimes you need to console log the result of that function. And I'm going to console log and see what is my data inside my system, what's the derived data that depends on the signal, but most importantly, what's the data that my user is seeing at the DOM. So let's go for it. So as a representative of the lazy signals, I picked Svelte runes because they are the ones that are like making a lot of noise about signals, and they have a good implementation, and they're actually quite similar to the Solid implementation with eager signals, but they chose to go lazy. So let's see. Now I'm going to update my click, and you're going to see in the console log the current value. So my click goes to 1, but I see 0. And that's actually not a glitch. What happens is because the signals are lazy, they had to schedule it for later, which means that by the time the JavaScript loop reaches my console log, it hasn't updated yet. The user is none the wiser, but my console log is always a step behind, which means that if you add a debugger to your function, in my opinion, things are not going to behave as you expect, because if I'm writing vanilla JavaScript and I updated a value, I want to see the value. Right. So let's go to Solid. That's a spoiler, sorry. Let's update. And so now we have my console logger, and it's just, I didn't show you the Svelte implementation, which is pretty minimal. Thanks to their compiler and stuff, that's how you declare a signal. I think that's how you declare a derived signal. Everything's working, so it should work, right? It should be right? And then on the on-click, I'm just pretty straightforward. The only thing is that it doesn't work the way I expect it to. I'm sure they have very good reasons for it, but it's just not how I'm looking for it. And then in the solid one, I create a signal, and then to create a derived signal, it's a little bit more verbose because we don't have a compiler, but then you just declare a new accessor, which is a function, and we call that signal, and so on. So because all the components are inside a reactive root, that means that the system is going to be able to track it. And then I set the count, and I log it. So now, as you can see, because I don't do the ticks, and I'm not batching them, the scheduler is very eager. So I get the update, and I immediately trigger that update so I can immediately access it. So if I add a debugger here, things are going to work just as they would in a vanilla JavaScript situation. Awesome. So we're about to run out of time. But I guess that was the last thing I had to show you. Now, that's in practice how it works. But then maybe you are one of those people that chose signals because of performance reasons, because it is a side effect of all these optimizations and all this way of handling all these efficiency measures that signals have, that they are significantly more performant than the alternatives that are out there. And if you are that, there is another difference between lazy signals and eager signals, where it's how your component tree is. There is a difference between if your component tree is deep, which means not that you have a bunch of nested components, but if not only that, but if the components depend of the state of the parent, in a very nested level, that's a deep component tree in this case. So lots of dependencies. Or wide, where you have the data, most of the times it's hoisted, and then you have a bunch of components that are deriving from that data, but they don't go deep, they usually go wide. So lazy tend to be more performant on deeper trees because of the way that they update in layers. So that means their memory consumption footprint tends to be smaller. In this case. And for eager, it's more when you have a bunch of interdependencies, or if you have a wider component tree, that also, so then the eager takes a little bit of advantage. And in my experience, what I've seen out there, most of the web apps we have out there, most of the apps we have out there are actually wider than they are deeper. We don't have deep nested derived values usually. But there's another plot twist to this talk. So I've been talking about lazy or eager, and actually Solid kind of cheated on that, because Solid is hybrid, which means Solid is eager for the end user, but internally there are a few heuristics that can determine if the data should actually be scheduled. So we have the batch, but internally we also can do some batching inside Solid, which means Solid is eager by default, but in some cases, because of performance reasons and because of consistency reasons, Solid schedules a certain calls. For the end users, if you're not going to go deep into contributing to Solid or writing a library that deeply changes something in the reactivity tree, you consider Solid eager. And that's what we're sticking with. But full disclosure, it's hybrid actually. And so that's about what I had for today for you. There's one more thing if you got interested in it. We at the Solid are actually about to start in 2 weeks SolidHack. And SolidHack is going to be a 1 month event, I think. Yes? Yeah, 1 month event that starts on 1st of October. There are some prize money involved. We've been sponsored by Netlify and Sentry. So there's about $15,000 in prizes. And the thing is, you just go in there, and there are going to be a few categories. You create a nice open source library, usage, example with Solid, and you're in it. If you're getting started with Solid, there is right down there Discord invite, so jump in. We in the Solid team are not able to participate, but we are able to help. So you can just get in and ask us some questions, and everybody's going to be super happy to help you. And as a consequence, you can get some money, hopefully. And thanks a lot, What the Stack. If you want to feel free to grab me on the coffee break, or find me in social media, and I'll be happy to chat with you.
Thank you, Atila. We have a question for you. So are you ready?
Yeah, sure.
Sure? You ready? Okay.
Yeah. So we have questions. We have time?
Yeah.
Awesome.
No,
I cannot
no
see.
picking. Come on.
Okay.
Like my wife, when somebody's ringing, she's like, who was that?
Yeah.
None of your... Yeah, anyway. So, what would you recommend going with a state... when would you recommend going with a state management lib opposed to using just signals?
Oh, that's a good question. So, so signals are essentially the primitive. So even if you are in Solid and you're going to go like with something that's more complicated, you can bring in a lot of any state management. Like most of them kind of work. Everything that works with JavaScript can work with them, and we have ports from most of the React state management libraries because of the thinner abstraction layer of Solid. Actually, every time you want to port a library to Solid, you just need to get the right mental model, and then it's just about deleting a bunch of code. So we have a few like XState that if you're like interested in what Eric just showed before, which is kind of mind-blowing. XState already works. They already have a SolidJS adapter. So you can use them. The thing is that Solid is going to allow you to have more reactive primitives. So you have the signals, and if you have like more complex objects, you have the stores. They're for like arrays and objects. So you can have deeply fine-grained reactivity to them. Actually, Daniel on the next talk has a very cool demo about some very complicated app that does super fine-grained reactivity stuff. So you should keep an eye on that. I heard that Q&A makes him nervous, so you should ask him some questions about it. But yeah, that would be awesome.
Thanks. No more questions.
No more? Okay,
yeah.
So as whoever made this question, come up and I'll have some stickers for you, and everyone else that has questions, I also have some stickers if you're interested in it. I'd love to chat with you.
Okay, thanks. Thank you very much.
Bye-bye.